So yesterday, we talked about the ratios of areas and volumes. And I gave you that worksheet, something like this, online. I want to talk about some of the word problems on the bottom of that worksheet. Start with number 8. The wastewater technology. We have a pipe at a sewer treatment plant, 75 millimeter diameter. Discharges 1,000 liters given period of time. It doesn't say what that period of time is. We want the pipe to discharge 3,000 liters, so we're changing the size of the pipe. We want to know what would the diameter of this larger pipe be. First thing we have to do on this type of problem is figure out, is this a ratio of areas or a ratio of volumes? And at first glance, in this one, it looks like a ratio of volumes, because liters are capacity, which is related to volume. Unfortunately, we can't change the volume here. All we're changing, when we change the diameter of the pipe, what we are changing is the area, the cross-sectional area of the pipe. We're only changing it in 2 directions. We're not changing that 3rd direction. The depth in this case would have to be a flow rate. You'd have to change the 3rd dimension. You actually have to have the fluid coming out faster. We can't change it. All we're changing is the size of the pipe itself. So this is actually a ratio of areas. So our ratio here, 75 millimeters squared is our length. X squared is our new length. Now, what we really did there was the ratio of lengths was 75 to X. We squared that ratio, 75 squared to X squared. Those squares are there because we are relating this to an area. 75 millimeter diameter gives us the 2,000 liters per unit of time. We want to change that to 3,000 liters. So when we cross multiply here, we're going to do 75 squared times 3,000. Squared gives us a huge number, 16,875,000. Has to equal, we cross multiply this way, x squared times 2,000. That's just 2,000 x squared. Now we have to solve that for x, a little bit different than the equations we've worked with before. Still works the same. We have to get rid of the 2,000, so we're going to divide by 2,000. So I'm going to take the 16,875,000 divided by 2,000. Give us 8,437.5. X squared. Now, how do we get to x by itself here? Square root, exactly. Square root of that previous answer. 91.855, 91.86 we're going to call it. Millimeters. So we need a diameter of 91.86, probably call it 92 millimeters. Take that flow from 2,000 liters up to 3,000 liters in the So again, that is a case where it looks like it's a volume because we're talking about volumes with the liters, but all we are changing is the area, so it's a ratio of areas. Number 9, we've got a square bar of steel, 38 millimeters on the side. Has a mass of 22 kilograms. What is the mass of another bar the same length? 19. What do you think? Is this a ratio of volumes or a ratio of areas? All three dimensions, or do we just change two? Two. We change the height, or the width, whatever you want to call it, from 38 to 19. Change the length from 38 to 19. But the overall depth, or whatever you want to call it, the length of the bar is the exact same for both of them. That didn't change. So because that third dimension did not change, this is a ratio of lengths. So our ratio of lengths, 38 to 19. We're going to square that. Squared is 1,444. 19 squared is 381. That's our ratio of areas. So then our mass, the larger one was 22 kilograms. Find our new mass, we're going to cross multiply and divide here. 381 times 22, 4. 5.805 kilograms, that new mass. Now I could go on with those calculations, but you guys get the picture. What you have to look at, even though mass is related to volume, you have to look at what's actually being changed in the problem. How many dimensions are being changed? Only 2 dimensions are being changed, it's still only a ratio of areas. 3 dimensions are being changed, it's a ratio of volume. Any questions on the rest of that worksheet? See the problems you'd like to know the answer to? Just no. So today, we're continuing on with that packet from last week, the one that had all the operations with measurements on the front. And then the bottom, we had the to the nearest 16th, 32nd, 8th, and all that. We're going to start looking at aspect ratios and tapers. An aspect ratio, sometimes referred to as a slope on a drawing. Anytime we have a surface that runs at an angle, there are 2 different ways to define it. One way to define it is to define an angle somewhere. You might define that angle as a certain number. That's one way to define it. Or we might define it with an aspect ratio. That aspect ratio looks like this. Telling us how many units of vertical movement we have for so many units of horizontal movement. In this case, there's 3 units of vertical movement for every 5 units of horizontal movement on that surface. So we have the full sides of 48 and 38 here. And on the left here, we have that side is 17 millimeters. And I ask you, what is this side here? Call that X. Find that, we're looking at this triangle right here. Now I get asked, well, can't we put the triangle on the inside? Sure we can. It means exactly the same. This dimension over here is going to be the exact same as this one here. And of course, this one up here will be the same as this one. It really doesn't matter which direction we make our triangle. I'm going to label this A and B for now, just so we have some dimensions there. Do I know either, or can I calculate either of the dimensions A and B directly right now? Sure. I know dimension A is how much? Oh, it's 21. You got it. 38 minus 17 gives us 21. Perfect. Now that we have that dimension, look at our aspect ratio. Now I can put 3 to 5, 5 to 3, either one. Doesn't matter what order I put them in, as long as I'm consistent in both sides of my proportion. 3 is the vertical or horizontal in that aspect ratio. Vertical. So A or B, which one of those is my vertical dimension? A, and we know that that's 21 millimeters. We're looking for dimension B then here. So we can cross multiply and divide. We get that B has to become 5 millimeters. Now we can find X by simply subtracting 48 minus 35. That's how aspect ratios work. Similar to an aspect ratio or a slope is a taper. Tapers apply circular objects with changing diameter. What it measures is the change in diameter per foot of length. Units for a taper is typically inches per foot, with the change in diameter in inches per foot of length. So when I have a taper, it looks something like that. Now let's say that this is 9 inches long, diameter of 2 3/4 inches. Down here, diameter of 1 1/8. Calculate a taper, T, equal to big D minus little d. That's the big diameter minus the little diameter. So here, the big diameter, 2 3/4. Little diameter is the 1 1/8. Over the length, divided by 12. Here, the length is the 9 inches. The divided by 12 is to convert the length into feet. The length is already given in feet. We don't have to do the division by 12. Here we'll have quarters minus 1 1/8 divided by 12. 2 3/4 minus 1 1/8. 5/8. 9/12 is 9 divided by 12 is 0.75. Divide those out, we get 2.166666. So we're going to 2.167. That's our taper. That is inches per foot. So the diameter on that piece changes by 2.167, that's actually 2 1/6 inches for every foot of length. Several aspects of the machining industry. Chrysler used to be a big one that had standard tapers for some of their parts. They have standard tapers. One of the most common one is the Morris tapers. Not Morris as in Morris the cat, but Morris is like Morse code. Morris tapers were a set of standard, you'd say number 4 or number 5. That was a standard number of inches per foot. Now let's just say that we need, most of the Morris tapers are really small, by the way. It's like 0.6 inches per foot and stuff like that. We will look at a couple of problems before we're done here with standard Morris tapers on. Let's say though we need 0.625 inches per foot is our taper. I've exaggerated my drawing a little bit here. But we have a leg for a machine. We need to have 1 inch diameter on the part that goes on the ground. We want the 0.625 inches per foot of taper, and this leg is going to be 8 inches long. We want to find the big diameter. Taper is big D minus little d over L divided by 12. We know the taper here. We know T is 0.625. Don't know big D. No, little d is 1. L is 8, so that's 8 divided by 12. Now we're going to solve this. Here's one where I probably wouldn't want to divide out the 8 divided by 12. It's going to give me 0. I'm just going to treat that as a fraction, and I'm going to multiply by 8/12 on both sides. We got 0.625 times 8 divided by 12. 0.4166666. 0.41667. That is, remove the 8/12 from the bottom of that right side. All that's left there is d minus 1. Solve it. 1. Big diameter is 1.41667 inches. Questions? 0.41667, I believe, is 5/12. So 5/12. We've got a V-notch cut in a block here. want to know what that distance is. A couple minutes, see what you come up with, then we'll take a look and see if you're on the right track. Types of problems are really an exercise in picking the problem apart, finding missing dimensions. The key to this problem is figuring out what the dimension is across here, which is how much. -90 minus 30 and then minus another 24. Now, the real key to this problem is realizing that since both of these are a 2-to-1 slope or a 2-to-1 aspect ratio, that cuts this VU edge in half, making this dimension how much? That's 18. 2-to-1 ratio makes this height here, the B, how big? X is questions there? Have a little fun here then. We've got a rod sitting in a groove. This is a right angle here. This is, oh, let's give it as 50 inches. And we'll give this 0.750 inches. Our ball diameter 0.750 inches. Here's what I want to know. How far does that ball stick up out of the top of that groove? That rod, I should say. But when we look at pieces like this, look for things that we know. We know that if the diameter is 0.750 inches, the radius is how much? 5 inches. Also a radius. So this tells us two things. One is that the center of that rod, somewhere over here, past that 0.25 inches. This radius that I want to look at more closely. I know that this is 0.375 inches. I know that this hypotenuse, the radius of a circle, and that circle is tangent to this surface right here. What do we know about the relationship between a radius of a circle? I have to go way back a ways to get to your geometry if you've had it. Radius of a circle is always perpendicular, always makes a right angle to a tangent if the radius is at that point of tangency. What that means is since this is a 2-to-1 aspect ratio on that surface that intersects, that means the hypotenuse of this triangle, remember at the end of last semester we talked about perpendiculars have the opposite reciprocal slope? That's why we weren't just exercising that to do generic algebra. There's a reason. So this intersecting surface here, if it's perpendicular to that surface, its aspect ratio is the reciprocal. The vertical and horizontal switch places. Now, here's the part that's tricky. We have this 1-2 aspect ratio here. That's a right angle. Vertical and horizontal always form a right angle to each other. So I'm going to turn that aspect ratio into a right triangle. And I'm going to find the length of its hypotenuse. How would I find the length of that hypotenuse? got one squared plus 2 squared. I'm just going to do the square root of that rather than doing a squared plus b squared. The square root of a squared plus b squared. So that is the square root of 5 is what that comes to, I believe. 2.236. What this does now is this gives us, this aspect ratio gives us a right triangle that is similar to the larger triangle. I'm going to call this dimension here E. I'm going to find dimension D. What side of the aspect ratio does D correspond to? 1. It's vertical, and the 1 is vertical. Now I need a side in the same triangle as D that I know the length of. That's the 0.375. What side of our aspect ratio triangle does that correspond to? Cross multiply and divide here to all this is 1 times 0.375 divided by 6. 1.677 is D. 0.1677. That dimension. So over here, that's saying this is 0.1677. We're going to have to redraw that whole thing a little bit bigger. E then is going to be found. E compares to what side of the aspect ratio? 2. And of course, the 0.375 still compares to the 2.236. Cross multiply and divide there, we get that E is 0.3354. Right? Let's look at what this is telling us. Here's my rod. 0.375. I'm going to leave the inches off just to make more room, but we know that that's inches. We have this triangle here. This side is 0.1677. This side is 0.3354. Which is telling us a couple of things. One is the distance from here, that point of intersection, 0.375 plus 0.3354. $7,104. That distance to the point of intersection. That's telling us the distance from here to that point of intersection. Remember, this was 0.50. So this has to be 0.7104 minus the 0.250, 0.4604. And so far? Which means then the height, that point of intersection, if this is a 2-to-1 slope, is going to be 9,204 inches. Problem there, I said this was only 0.75 inches tall, didn't I? We're gonna have to modify that. Make it 1 inch tall, exactly 1 inch tall. Otherwise, that point of intersection would be above the top of the part, or it would be hitting the surface with it. It's that high up to the intersection. So if it is 1 inch up to here, 0.9204 up to there, how far is it up to this point here, up to the center of that rod? What am I going to add to the 0.9204? Perfect, 1677. 0.0881. And then from center up to the top of the rod, how much is that? 5. Still doesn't work out really the greatest because this here actually is above the top, but we're going to pretend it works. So that total height, what this is saying is the total height from the bottom up to the top of the rod is 1.4631. So then we can find this height above the surface is just the distance, 0.4631 inches. Like I said, I tried to make that one up on the fly, and I didn't do the greatest job putting good numbers. You guys get the idea of how it works? Key is to take this aspect ratio and treat it as a right triangle and find the length of its hypotenuse. That way you can compare it to other slope lengths. Okay, so if you still have that packet from last week, we're continuing on it. And if you don't have that packet, I did linked it again to today's site in Blackboard. In that packet, I would like to have you do problems 31 through 39 and 42 through 45. Now, 44 and 45 are extra credit. Don't think I honestly expect you to be able to sit down and just blow through those. Those are really tough problems. Number 45, sometimes when I go to try it, I've done it several times in class. Every now and then when I go to try it, I can't get it set up right the first time and have to circle back. So those are, if you actually get those completed, show them to me, I'll give you extra points. This is homework, so you don't have to turn it in. But if you think you've got an answer for 44 or 45, show it to me and I'll give you credit for that. So you have work time here. There is a quiz out there. I'll post it on Blackboard. Does anybody rather have a hard copy of it? I can give you a copy. Give you a hard copy quick. I'm the recording here. That'll be due